Our speaker for today is Dr. Jayant Joshi. Dr. Jayant Joshi is a solar physicist and assistant professor at the Indian Institute of Astrophysics, Bengaluru. His research focuses on solar magnetism, spectropolarimetry, solar flares, magnetic reconnection, and chromospheric dynamics. Dr. Joshi earned his PhD in 2014 from the Max Planck Institute for Solar System Research, Göttingen, Germany. He has held postdoctoral research positions at Stockholm University, Sweden, the University of Oslo, Norway, and the National Solar Observatory in the United States. With that, I will welcome Jayant to deliver the lecture.
Thank you, and thank you for giving me the opportunity to speak here. So it's always pleasure to talk to in the very general sense what we are up to, what we want to study, right? What is the implication, where we are in our quest, right? And it is more encouraging to speak on Sunday, where most of people might be taking leisurely break from their hard work, but then there are a lot of enthusiastic people who want to spend their day on learning little bit about science, right? So it is quite overwhelming, right? So today what we're going to talk about is our sun, right? The space weather and what we are doing, the status of the astrophysics research in terms of studying the sun in India, right? So we are going to talk about that. So this is the sun, and then it is a rotating body. So you see the upper atmosphere, the corona there. Yeah. So what we're going to talk point by point today is general sense that how the energy is generated, because it is giving us the energy. So what is the source of energy in the star, right? So this is our in the Indian culture, the sun is considered as a god, right? It is giving us the light and life and the warmth, right? But sometimes the god can also get angry, right? And when it get angry, we have some kind of repercussion about that, right? So to know about what would happen when when sun get angry, at least we should know about how the sun looks like, right? So in general sense, so we should know our friend which is giving us energy to sustain the life on this planet, right? And little bit about solar cycle, which we will learn about detail, and then this is when the space weather come in, when we have an adverse effect of the event happening on the sun, right? So this is how the interior of the sun look like. So this is the central part, right? And this is where the most of the energy is generated. So it's mostly made of hydrogen, right? And then the 90% of this energy is produced within this 25% of the central part, right? And it burns almost like 6 × 10⁻¹1 kilogram of mass, right, every second. And it turn helium into the hydrogen into the helium nuclei, right? So we know how it happens is that we have 4 different protons, right? So the atom is made of the proton, neutron, right? So when this 4 proton actually fuse, so this is the process just opposite of the atom bomb, right? Where you split the atom. Here you are taking the part of the constituent of the atom, which is the proton, right? Fuse them together and create a larger atom. But when you created this larger atom, helium, the mass of the helium basically is little less than total 4 protons, right? So what happened is that, there was a 4, so helium is lighter than the 4 protons. So there is some mass which is lost, right? And this mass turn into the energy. This is the famous equation, This is the Einstein famous equation, A = mc square, right? So m is the mass, right? So when some mass is lost, that will turn into the energy. And that energy is corresponding to gamma rays, okay? And that energy, how it is generated in the core of most of the stars, but especially in the sun. So this photon generate here, then it travels up to the surface, right? Energy is generated, energy has to now come up to the surface, because most of the energy is generated in the central part, right? So this photon takes billions of years to basically travel from here to here, basically millions of years, because it's a dance. So it always collide with another particles, right? Change its energy, another wavelength, and keep traveling. So it is called the random walk, right? So here the energy is generated, now it passes through the radiation. Radiation is basically what? Light, right? but then the upper part become very opaque for the radiation to pass. So, if energy is not allowed to pass through the radiation, right, then it's become the boiling pot, right. As we put the heat on the bottom of the pot, right, in a liquid, when the energy is that is also basically heat. That heat we cannot pass directly, then what happens that the liquid start basically do the convection, right. So, the hot part will start rising up, then it cool downs and go down, right. So, this is bubble what we see, this is what exactly happen in the top part. So, these cells actually start doing convection, and that is how the energy actually reach up to the surface, right. So, this is, I do not want to go into detail, but doing the modeling and knowing the property on the surface, now you can know what is the temperature at the center of the sun. So, this is the center and this is the surface. So, in the one dimensional, if you see, it is up to 15 million Kelvin hot at the center, which allows to the proton to fuse, right, and do the fusion reaction, right, and then it drops toward the surface. So, it is just in the number, I am not going to speak individual number, but you can see that how massive our sun is, its radius, right, average density. So, average density on the earth is basically 5.5 gram per centimeter cube, right, and average density on the sun is, so it is not as dense, it is a gaseous body, right. So, 1.4 grams per centimeter cube. Also, the core density is in the earth is much higher compared to the core density at the center of the star. Its age is almost 4.5 billion years, right. This is the distance. So, these are the just number, and it rotates around its axis, at the central axis, that earth rotates around its own axis, right. The same way the sun also rotates, and it takes around, on average, takes the 27 days. Okay. So, now this is the interior of the sun, right, how the energy is generated, how it passed through in the general sense to the surface, but then it comes called the atmosphere of the star, right. The same way that this is the surface of earth, whatever above it, everything is called the atmosphere. The same, there is a surface of the star where the light cannot escape below, any light, any photon below that surface cannot escape the sun, right. So, wherever the light able to escape, that is we call the surface of the sun, that is called the photosphere, right. Most of the photons are coming from there, and then it has a chromosphere, transition region, corona and heliosphere, right, which we look into. So, if we take a temperature from the surface of the sun, right, and go away from the surface, this is how this temperature changes. So, this is height in the kilometers from the surface, right, visible surface of the star. So, as we see from any normal telescope, whatever we see from above that surface, how the temperature changes, right. So, you see that this temperature is basically around 5000 Kelvin or something. So, this is in the log scale. So, this is actually 10,000, 100,000, something like that, 1 million, right, temperature. So, first the temperature started decreasing, that we understand there is a source, right, we put a candle, right, and we are very close to candle, we feel the heat. As we start going away from it, the heat reduces, right. So, it started reducing, but something happened strange on the sun, that around 500 kilometer from the sun, temperature started rising, and then there is a sudden rise in the temperature, and in the upper layer of the sun, which is called the corona, temperature suddenly become 1 million Kelvin temperature, right. And this is one of the biggest puzzle in the solar physics. Most of the solar physicists is trying to understand what is happening from here to here, that why suddenly the temperature has increased to the 1 million Kelvin temperature. Okay. So, that is the one of the, and that is why we study the sun, right. So, one is that it has an implication to what is on the life on the planet, right. But then we want to study the sun because we are curious about the nature, right. So, want to study that why the sun has a sunspot, why its temperature is 1 million Kelvin temperature in the corona, right, how it evolves, right, what is the periodicity, does it change in the long time scale. This is all we curious, and if we can understand certain things about sun, we can go and look into the other stars and try to understand that, because this is our closest laboratory, right. This is our closest plasma laboratory, which can observe in much more detail. The star you will observe as a point source, right, a dot in a sky. But sun you can resolve it because it's much closer. So you can resolve the whatever physics happening there and understand what would be happening to the other stars, right? So it is divided in this general terminology. So this area up to 500 kilometer, it is called the photosphere. The region above that, it is called the chromosphere, where the temperature is around 10,000 Kelvin. Then suddenly there is a jump from 10,000 Kelvin to the million Kelvin temperature, and that is why it is called the transition. It's called the transition region because there's a huge transition in the temperature, right? And it's become the million Kelvin temperature. So this is how the surface looks like, right? So this is called the photosphere. And then you can see that what is the most visible features when we see the surface. This is the basically dark spots, right? Mostly it is featureless. If you look into this resolution, right, it is mostly featureless, but you see this dark blemishes, and those are called the sunspot. And when the Galileo made his telescope, he was almost 450 years ago. He observed the sunspot, right? He was the first person to maybe there were sometimes you can see the sunspot by the naked eye. Sometimes the sunspot is very big if you have a clear sky, right, and immediately after the sunrise or just before the sunset, right, if you know that such a big sunspot is there, you can look through by the naked eye and you can spot but then you have to know it, right, that there's something like that. And it would be very rare that without the telescope people knew about that much, right? People might have spotted, but there was no statistical probably evidences that this kind of feature might be appearing. So this was the Galileo who observed it. And then above the layer which come the photosphere. Now you see that whatever you were seeing in the photosphere, it has dramatically changed quite a lot, right? It was photosphere almost featureless but big spot, but now here you see this dark elongated structure, right? Many bright features here, right? Something like that. So these are called the filaments, right? These are the bright features where the magnetic field is high. Sunspot is also where the magnetic field is high. So you see that when you go little bit above in the atmosphere, there are more features, right? And now if you go to the corona, it's become really beautiful, right? You have all the loops. Yeah. Yeah. So so if you go here, basically, so whatever color we put is the artificial color. That right? Our detectors are not color, right? So they will detect, and we kind of assign a color depending on some physical meaning, sometime and sometime no meaning, right? So here it is in the black and white. But if you want to show really the color that we know that our sun looks yellow, right? So you would put, because it has a temperature which is around 5,000 Kelvin, right? So 5,000 Kelvin temperature is basically in the visible band fall around the yellow colors, right? But then this is also the similar color because chromospheric temperature is not so off from the photospheric temperature, maybe a few thousand Kelvin higher. So then this color actually justifies. So this looks like a yellow ball, right? Now here color actually, the next movie, the color is basically fully artificial, right? It doesn't signify anything in terms of the electromagnetic spectrum because this is not in the visible range, right? This is UV, and UV you cannot see, right? So you cannot associate with any color because color means the visible part of the electromagnetic spectrum which we see in the rainbow, right? Correct? So this is, but this is a particular species iron line. So basically it requires very high temperature. The temperature here is basically 10 to the power 5 Kelvin. So you can say 100,000 Kelvin temperature, right? Or almost close to the million Kelvin temperature because it's 6. So this is very hot, right? And now you see that this loop like structure, right? Here, these are all magnetic field lines. So the plasma is trapped into the hot magnetic field lines, right? So hot plasma is trapped into the magnetic field lines, and that's why they look like a loop.
Sorry.
Yeah, yeah.
So you have marked out different zones in this graph, right? So apart from the temperature and the distance, what other properties?
Yeah. So for example, their density would also change. right? So the gas density, for example, in the Earth atmosphere, you go from here to, right, then go higher in the atmosphere, the density is decreasing exponentially, right? The same way when you are in the atmosphere, the density would decrease. So the photosphere is very dense, right, relative to what you see the density here, for example, right? Then there, if you go into the proper physics, then the ionization of the atom. So ionization, what does the ionization mean? So for example, if you have a hydrogen has a 1 electron, right? So if it stay with the atom, then it is non-ionized. But if you remove the electron from the atom, it become ionized, right? To ionize, you require a lot of energy, right? Here the temperature is million Kelvin temperature, right? So this basically signify the ionization, right? So this is iron 9. So that means the 8 electron has been removed from the iron atom, and for that we need so much energy. That's why we know that why the corona is million Kelvin temperature, because to ionize you need that much of the energy, right?
Sorry, I have so
Yeah,
how
yeah.
do you differentiate or measure at such large distances? Like these are very sensitive properties, right?
Yes. So this is what we measured, right? When you are observing here, what we are measuring? We are measuring the photons, right? Okay. Right? We are measuring the photons, but we just don't make the images, right? We take the spectra, right? The spectra has a finger. These spectra are the fingerprint of the star, right? So for example, this particular iron 9 line, right? It will show into the emission. So there would be lot of lines. If you know about the Fraunhofer lines, what are the Fraunhofer lines, right? If you have a hot material, right? If you have a sodium lamp, right, and you put a sodium gas in front of it, it will make a transition and you will see the two dark lines, because whatever transition happen into the sodium atom, right, it will absorb this particular wavelength, and you see in the end the dark absorption line, right. So this is what, so this material, this all helium, hydrogen, iron, calcium, magnesium, all these elements are present in the atmosphere of the star, right. Now when the light pass through, they will turn into this spectral line. This spectral line would form in particular condition, right, certain temperature, certain density. So if you observe them, you can kind of infer that what would be the temperature, what would be the density, like that. Okay. So now we go even hotter. So this is 6 points, almost 1 order of magnitude brighter than here, right. It was 10 to the power minus 5, here 10 to the minus 6. When you go to that temperature, right, even higher temperature, you see that earlier you were seeing the larger loops, now you see that only certain part of area are very hot, not whole thing, right. And that shows that only there is a multiple temperature in different region, and now you see that there is a completely dark here. So it is not a uniform ball, right. It is not uniform that everywhere temperature is same. It is changing and it depends on the magnetic field, because if you look into the magnetic field, now this is the magnetic field map, right. So what you see, where it is gray, it is almost 0 magnetic field, close to 0, it is never 0, close to 0, right. And when you see black, that means the magnetic field is going toward the surface, okay. And when you see the white, the magnetic field is coming out of the surface. So when you see the loop, the magnetic field from the white, it is coming out, and the black, it is going back, right. And that was what you see in the coronal lobe. And if you see the brightness, which was the million Kelvin temperature, there was more bright here where there was a magnetic field. So it is highly associated with magnetic field. So the sun is a plasma laboratory where you can understand the interplay between the plasma, right, and the magnetic field. So this is called the domain of magnetohydrodynamics. The hydrodynamics is the fluid, basically the plasma, and the magnetic field. So how they control each other in this stellar atmosphere, right, that you can study. So now I show you the photosphere with a huge gray image, right, with only spots, right. Now I take a bigger telescope and zoom into the small area, right, and this is how it looks like. So this is convection. This is your boiling pot, right. So this is exactly that. So whatever you see, the bright central part in the bubble, it is where the hot plasma is coming up, and the cool is basically when it gets cooled down, it's go back to the surface. So this is the boiling part of the star, and then it's again related to the magnetic field. Then there are spots. So again, I take when you saw this full image, you saw the spot was like a dark part, but now I put the big telescope and zoom into the spot, then you see that the spot has a lot of fine scale structure, right? So it is not just, so it has a very central dark part which is called umbra, and then the surrounding part which is called the penumbra. This penumbra has these fingers which is called the filamentary structure, and this has a very particular plasma flow which is always going away from the center of the spot, and that is called the Evershed effect, and that was discovered in the Kodaikanal, right. So, I will come to that Kodaikanal part, but this is how we study. So, we also want to just do not want to know that what is implication of energy and particle and radiation released from the sun and what is implication on earth, but we also want to know what is happening in this kind of features to understand their nature, right, because this is nature. And we want to understand what is just nature of the human curiosity, that we want to understand whatever going in the nature. So, for example, whatever the plasma and magnetic field interplay is there, we want to understand that, right. So, this is the loop, right. If I zoom in now to the coronal part, right, then you will see this loops, right. So, where one foot point have a positive magnetic field is going and connecting like here, right. So, this is, and these are filled with the hot plasma, right, and this is the building block of the corona. So, everywhere if you zoom in with the large telescope in the corona, you would see it is not a blob of the hot plasma, but it is highly structured, right. And what makes this a structure, that is another field of the research, right, we are interested. So, I just want to show that just studying the sun, fundamentally we have also discovered a lot of things in the physics. For example, helium. Helium was not known before people started looking at the spectrum of the sun, right. So, helium was first discovered in 1868 eclipse. Actually, the same time there was also expedition was happening in India, and that they did not able to report it before this people, but the helium was also discovered actually from the Indian soil as well. And then they found this new line at this particular wavelength, right, observed during this eclipse, right. So, they saw that okay, this particular line in the spectrum, what we know from the earth, we cannot explain it, there must be some new material on the sun, right, and they call it coronium. But later it was recognized that this is the iron 13 line. So, iron 13 means again that 12 electron has been 13 electron has been removed from the atom, right, iron atom, and that people understood that you require a lot of energy, right, to remove this 13 electron from the atom, iron atom, and that people came to derive that the corona must be very hot, right. This is how people learned that why the corona should be million Kelvin temperature, because they observe this particular line, right. Now, that is when we were looking to the images at the particular time and something, but then sun has been there for a long time and it might have a certain property and varying with the time, right. So, if you start looking at the number of sunspot, so every day you take an image, right, you see the sunspot, you count how many sunspots are there, right, and then you plot against the time. So, from 1880 to 2020, and then you see that sunspots are not always same, right. You see that there is a up and down and up and down. So, one peak to another peak, on average this is the 11-year difference. So, after every 11 year, right, number of sunspot increases to the highest number, and then at certain point it is almost come close to 0, does not go exactly 0, but very minimum number of sunspot, right. And then if you plot where they are appearing on the disk, right. So, 0 is the equator, right, this is the latitude. So, 0 and the 90° is the pole, right. So, where the sunspot are appearing with the time, and if you plot their position, you see that beautiful pattern which looks like a butterfly, right. So, this is called the butterfly diagram. So, we know that when the cycle begins, so this is the beginning of the cycle, right, solar cycle, 11-year cycle. At the beginning it is appearing around 25-30° latitude, and when the solar cycle ends, it's go close to 0°, right. So, they appear at the particular location, right, and they follow the pattern. So, now this helps us, people who are trying to model how the magnetic field is generated inside the star and why it is varying 11 years, right. So, if you are trying to do the physics, if you are come up with a theory, you have to explain the observation, right. What you observe is your theory is able to explain observation, then your theory is good and beautiful, right. If your theory is not able to explain the observations, what we see in the nature, then your theory is maybe not the good theory, right. So, the people who try to model how the magnetic field is generated, they try to reproduce this kind of pattern and this cycles, right. Now, from the cycle to cycle also you see that some particular cycle, the number of sunspot was per day was quite high, some cycle it was very low, right. So, why the number of sunspot from cycle to cycle are changing, that is also field of research. People trying to understand that why from the cycle to cycle, some cycles are very strong, some cycles are very weak, right. So, now we go toward the angry part of the sun, right. So, this is the flare. So, you see now there is a sudden explosions are happening, right. So, you see there would be explosion here, big explosion, plasma falling back sometime, right. This is another explosion here, you see the sudden brightenings, you see this explosion here, right. So, this all called the flare. So, this is another explosion. So, this is of the release of the magnetic energy, right, which I will explain. So, there is when the sunspot appears on the surface, sometimes they get twisted, is like a rubber band, right. So, if you start twisting a rubber band up to certain angle, it might break, right, it will release, right. The same way when the magnetic field get a tension, right, it want to release its energy, because now that this twist is putting excess energy into it, right. So, it will try to break out of it, right. So, now, but flares are also different categories, right. You might heard, if you are looking into now, if you are active on the social media and following the science, then suddenly you will see that, oh, X class flare happen, and then it could be hazardous to the electronics and the communication and everything, right. So, there are different kind of flares, and they have defined depending on how much radiation they emit into the X-rays. So, sun emits radiation from X-ray, because it is almost kind of a black body, to the radio waves, right. But during the flare, this radiation in X-ray is excess radiation will come. So, this is a plot of the X-ray radiation. So, you see that this is normally you have a certain variation, but at certain point there is a certain spike, right. On those spike in the X-ray radiation which define the flares. So, X class flares are the very strong flares, right. And recently in this year there had been tens of X-ray flares has happened. So, if you follow the social media about science, right, you will come to know that whenever flares are happening, and you will see the lot of news about it. Now, the coronal mass ejection. So, as I showed that you see that coronal mass ejection more often are associated with flare, not always, right. So, you see that there is a flare happening here, right. So, at this part you will see the certain brightening and ejection might be happening, and you see that after some time you see something is ejected from there. So, in the quiz, if you were there in the quiz, the coronagraph image was shown, right. So, this is similar coronagraph image, right, where the sun disk is basically, yeah. So, you see in the coronagraph image, you have seen that there is a large ejection of the mass, right. So, you will see the ejection of mass going from here, something like that, right. So, this is called the coronal mass ejection. So, there is a tons of material basically ejected, sometime associated with the flare, sometime not associated with the flare, but that is propagate into interplanetary medium. So, that propagate through the solar system, right, and might arrive sometime to the earth, because sun is of course is a spherical body, right, and earth is here and the CM is happening, it might not come to the earth, right, it can go into the another direction, but sometime it can propagate toward the earth and then affect earth atmosphere. So, just to continue which happens. So, for example, there are a lot of sunspots. So, whenever flare happens or the CME happen, they are also associated with the sunspot. But now, solar physicists are trying to understand which sunspot will generate a CME and the flares, and that is also a very active field of research. So, people try to understand the property of the sunspot, its property of its magnetic field, right, and then see that, try to put lot of property into the analysis and see that what kind of sunspot would generate the CME and the flares, right. Because if they have adverse effect on the Earth atmosphere, right, so it would be better that if we know in advance, right. It's like a weather on Earth, right. If the cyclone is coming, it is would be, if you want to evacuate the people from the coast, it is always better that if you can predict when the cyclone will happen, right. So you have a time in hand to predict. So there are a lot of, we don't understand right now fully, right, which sunspot will generate the CME or the flares, but there are a lot of research going on. People are also trying to put the machine learning techniques and the deep learning technique, artificial intelligence into it, because there's a lot of data. So if you for example, like if you have a training, right, in the machine learning, what you do is like you have a picture of a dog and cat and you give it to computer and want to predict that it is a dog or cat, right. Now if I give the thousands of image of the sunspot and say that train that this sunspot would flare and this sunspot would not flare, even I don't know what physics is happening there, but this artificial intelligence might learn that which one. So people are also trying to use advanced technique to predict what kind of activity would be associated with particular active region of the sunspot. Now we come to the space weather, right. So space weather, the effect of whatever happening on the sun, right, how does it affect the life on the Earth or in general all the planet in the solar system, right. So one of the beautiful effect of this activity on the sun is the aurora, right. I think many of you have already know what is the aurora and you might have seen the pictures. So this is actually very early pictures, maybe around 1839, not the pictures, the drawing. So people start in the north of the Europe, like Sweden, Denmark, Iceland, Finland, right, and that region, people were seeing this kind of phenomena regularly because it happens close to the pole, right, and they were drawing. So whatever white structure you see, this is actually drawing of the aurora, right, in the older times. But if you take a picture nowadays, it looks like this. If you are at the right location, right time, right, then you see this auroras. And this is basically has to do something with the sun, right. What is happening on the sun and what is traveling from the sun to Earth, that's create the auroras, right. And if you take more pictures, and recently we able to see the auroras from the India, right. So this is just almost a few weeks back, 10 to 11 October 2024. This is the one of our, we have observatory in Himalayas called the Indian Astronomical Observatory in Ladakh, and one of our staff there who is also in charge of the observatory able to take this nice red hue of the aurora. So this is aurora, right. This is another picture, just the reflection of aurora in the water body, right. But it is very rare to see this kind of aurora from, because the Ladakh is around 32-degree latitude, so very far from the pole, right. So this means that is some very strong event might happen, and whenever the strong event happen, you might also able to see. I'm not sure that we have also seen this aurora in the May this year, right. Before that, I don't know 100% there is any recorded history of sighting the this year. But before this, I am not sure that there is any recorded history of sighting of the aurora from the Indian land. Yes, yes. So that's saying that this is probably the recorded in the history. Maybe there somewhere, if you know the Buddhist script and you read probably Buddhist script, somebody might have written somewhere that tonight I have seen some beautiful red colors, right? But then you have to search through that Buddhist script and see. And definitely, if happened now, definitely it might happen in the past, and somebody might have recorded somewhere. So that is another, not direct science, but another field of research. People look into the text, ancient text, and see older text, and see that people have reported this kind of event observing from the Tibet or the Ladakh or that region, right? Now you can also see it from the space station, right? Because now you are looking from the top. So these are the movies of the auroras seen from the space station. So this is the space station observing deck, and then you see the auroras, right, from the space. So this all green and red part is basically auroras happening. This is what you see from the space station. So if you want, if you one of this young kid want to become the astronaut, the one of the perk that you will be able to see the aurora like this, which you cannot see it from the Earth, right? And then it doesn't only happen on the Earth, it also happened on the other planet in the solar system. So somebody can tell me which are these two planets? Yeah, Jupiter and Saturn, right? And these are the polar region of the Jupiter and Saturn. As we see the auroras on Earth, we also see the auroras on those planets as well. Okay? So similar things are happening there. So we know that they are physics, and physics, if the conditions are similar, physics should be reproduce the similar observations, right? This is how you test the physics, right? Now, history, that how we knew that what is happening in the Earth in terms of the aurora, how we can associate it with what is happening on the sun and arriving it here, right? So we have to go a little bit on history, that how people learn about the physics, right? So we see the auroras and something happening on the sun, but how we connect with them, how people were able to connect these two things. So I'm going a little bit into the history. So 1850 in the London Kew Observatory, there was a magnetic field. So you have a magnetogram, you always measure the magnetic field. There are a lot of different observatories which measure the Earth magnetic field, right? So this is Earth magnetic field, and suddenly on the 27th August in this year, 1859, they observed the spike in the magnetic field, and the magnetic field has decreases, and then it recovered back, right? And then at the same time the auroras happen, people know, oh, two things are happening together. It is possible the both might be connected, right? So they start looking into the understanding why they are related to each other, right? And then this is the more modern observation from not modern observation, but the statistics of the observation. So this is 1865, so 2005. So when people started observing that there was a change into the geomagnetic storm. So geomagnetic storm is defined when the magnetic field of Earth suddenly changes. Okay, that is why the geomagnetic storm, right? So people immediately after that particular event, they started recording that what is the relationship between the geomagnetic storm happening on the Earth to what is happening on the sun, right? So what you can observe on the sun at that time is the sunspot, right? Simply. So on the top they have plotted the sunspot, right? And this is the frequency of geomagnetic storm. So they realized that whenever the activity, there were more sunspot, more activity, geomagnetic storm was more, right? So that itself in the beginning at that time people have concluded that, but now we have this statistical evidence for more than century, right? Almost 150 years now, and we can see that every time there is a peak in the sunspot number of geomagnetic storm on the Earth increases, right? So you statistically you know that there is a connection. One event you can say it is a coincidence, right? But statistically you observe the same phenomena, right? It's like a Bengaluru traffic become worse whenever it rains, right? But if you observe one, you cannot make that conclusion, but you live here and you see it every day, that's become a fact, right? The same way, when you observe for more than 150 years, you can establish the connection between that. You might not explain, this is just a connection, right? A event and the consequences of certain event, right? But why it is happening, why both are connected is still not known, right? So then at similar time, yeah.
Is there a pattern to how these things occur? Like somebody sat and analyzed the history and said that we can expect the next geostorm.
Yeah, that is the next geostorm is very difficult to predict, and that is the active part of the research. There are a lot of solar physicists spending day and night out to understand if they can say that in advance when the geomagnetic storm would happen. This is just plotted on, see, this is the 1 year timeline, right? It doesn't mean that geomagnetic storms are happening every day, that many, right? This is only 10 bars in 11 years, right? So they are average in a 1 year. But if it will happen today, or it will happen tomorrow, or the next month, that we don't know, right? So similar to, at the same time, in the 1859, Richard Carrington, and he has a telescope in his backyard. He was looking at the sun, and he was the first person to observe the white light solar flares, and that time there was no cameras. Whatever they used to see, they will draw, right? So he draw the sunspot. This is the darker part of the sunspot. I showed the high resolution images, right? The modern day telescope, and it has a lighter area around it, that is the penumbra that he saw. So, the very complex sunspot structure, but then he saw this two cashew like structure, right. You see this one. This was the sudden brightening which appeared only for the few minutes when he was looking and then disappeared, right. So, he realized that something is happening which is transient. Transient means only happening for few minutes, a very short time duration and disappear, right. This was the first observation he made during the same time, right. So, whatever event happened during time, people also started thinking, does it related to this, right. So, it is not related to the number of sunspot, but it is related to the what is happening in the sunspot, right. So, now if more number of sunspot, that means there is a more probability of flaring happening, right. So, it is not directly the consequence of the sunspot, but what is happening in the sunspot. Some sunspot might not flare and some sunspot might flare, right. So, this is what they observe. At the same time, this is the another plot. So, you see that what curve you are supposed to see is this one. So, there is a change in the Earth's magnetic field suddenly and then it go out of the I think limit of the detector where you can plot on the graph, right, because it is a plotting graph, it would detect and in the paper it will start drawing like that, right. But then it went out of the scale of the graph and then it recovers back, right. And then at same time happened when the Carrington observed this flare. Okay. At same event was also observed in the Colaba Bombay Observatory. Okay. So, there was an observatory of measuring the Earth magnetic field and the same time they also observed the sudden change in the magnetic field, in the Earth's magnetic field, right. Now, there is a report people have looked. Yeah, there is another. Sorry. Yeah. No, so yeah, so there was not immediately same day, right. So, whatever happened on the sun, it will the things arriving at Earth, it will take some time, right. So, it is not also fixed time, it is not, it is again like a Bangalore traffic, something leaving from the destination, you are going to the source and you are going to the destination, but it will not have a fixed time, it will depend on the traffic. The same way what is happening on the sun, what happened on the sun, what kind of vehicle it left from the sun and what medium it is passing through, right. It will take sometime take 2 days, sometime take 3 days, sometime can arrive within the 24 hours, right. So, immediately that people in 2018, people started looking into the literature and saw that in that particular event where people were able to see the auroras, right. So, this is the plot of aurora. So, it happens 2 days, 27 and 28 and September 1, 2, 3. So, you see that in that geomagnetic storm there was 2 dip, one was the very strong dip and one was the weaker dip, right. And these are all the points somewhere in the literature it is mentioned that people observe the aurora, right. So, you see that Australia, which is something like at this point which is almost 40°, right, where the aurora was sighted. So, aurora also in the Mexico, very low latitude, very close to the equator, going closer to equator, people started seeing the aurora. So, that would show that whenever a big event would happen, right, aurora could be also seen on the lower latitude. Now, how to connect it? Again, you have found the reason that something happening on the sun, we see the auroras here, but why they are related to each other, right. So, that is also related to how the physics developed with the same time, right. So, around that time in 1897, not a time, almost 3 decades later, Thomson discovered the electron, right. So, that is a very good puzzle for this geomagnetic storm and the auroras happening, right. Then a Norwegian scientist, Christian Birkeland, what he did is he tried to generate the magnetic field in a lab. So, this is mini Earth. So, he have tried to, the Earth magnetic field is start from the one pole and go to the other pole, right. So, he able to create a magnetic field in a spherical body which connect from, and then he put a gas like nitrogen there and then he bombard the electron. So, now the electron is already been discovered at that time. We take the electrons, he started bombarding the electrons in this, and then he said that when this electron travel along the magnetic field line and interact with the gas, it emits, right. So, he's found a connection. Okay, there must be some charged particle coming from the sun. We have a similar magnetic field, right? We have a gases in the earth atmosphere, right? So, when this very highly energetic charged particle travel along the earth's magnetic field, right, and interact with the atmosphere, it will emit, right. So, he able to, and this is the hypothesis in general is accepted until now, right. This is the general physics of the auroras happening in the earth atmosphere, right. And then again the sunspot was known, but sunspot was magnetic was not known, right. They observed the dark features on the solar surface. Some people thought that because it looks dark, sun has to be, so it's a hole on the surface of the sun and something is dark inside, so you see the dark, right. But later George Hell, he found that in the magnetic field is a Zeeman effect. If you have people who went to the physics courses might remember something about Zeeman effect, and people who will go to the physics courses, they will learn about the Zeeman effect in the future. But what happens in the Zeeman effect is the one spectral line, so this is the absorption line, wherever there is a magnetic field, it's become broader in the presence of the magnetic field. So, energy level in the atom splits in the presence of the magnetic field. That was discovered by Zeeman, and then George basically have demonstrated using the first time outside the earth that magnetic field can be detected using the Zeeman effect on the sun, right. So, this is how he detected the magnetic field. So, now we saw that, now we know that electrons are energetic when they interact with the earth magnetic field, right, charged particle, they can create the auroras, and now we know the sunspots are magnetic, right, they have a magnetic nature, right. At the same time in the 1921, you see that there were a lot of reports about this repercussion of the sunspot created with the rail tie-up, credited with the rail tie-up. The electric disturbances affect the French wires and sunspot aurora paralyzed wires. So, for example, so they realize that auroras is happening, right, some activity is happening, and same time it is an effect on the electric lines, right. So, there is some connection between what is happening on the sun and whatever the electricity grids were there, right. And then another discovery happened is the understanding of that the earth atmosphere have an ionosphere, right. The ionosphere is where the atoms are ionized, right, is in the plasma mode, and then Edward Appleton actually found that there is ionosphere, and that has to do with UV radiation coming from the sun, which make the ionosphere, right. So, I will just move ahead. Then in 1958, Parker, who is one of the most famous solar physicists, he said that he predicted there must be, even out of the flare and the CMEs, there would be a charged particle always coming from the plasma, might be flowing from the sun, and that is called the solar wind, which is all the time flowing, right. So, this is sun and the solar wind, this is the earth, this is the earth magnetic field, right. So, this is magnetic field, how it is connected, but we see the simple picture maybe in very early textbook, the other side it is not simply as circular as like that. So, this is the daytime, this is the night time, but then you see that this tail is much longer, because this wind coming from the sun actually pushes the magnetic field line and make a long tail in the backside. Okay. And this is just the animation. So, this is the sun, solar wind is coming, this is the earth, and because earth has a magnetic field, it is basically diverting the charged particle, right. So, it is protecting us. So, earth magnetic field, earth has a mechanism to most of the time protect us from this charged particle coming from the sun, right. So, you see that they are deflected. So, in the early 60s, what we understood from this all discoveries one by one, almost covering the half of the century or more, is that the sun has a magnetic field and sunspot has this 11-year cycles, right. Solar corona is million-degree hot, that people already knew in the 1960s. Solar wind, right, that also been known, Parker has predicted it, and large solar flares sometimes disturb the ionosphere and the radio communication. So, they know that radio communication was already existed there, and people realize that whenever there is a flare happened on the sun, people observe there could be after few days or some time there would be a radio communication can be disturbed, right. And the earth is surrounded by the magnetosphere, this magnetosphere, the magnetic field, which is in general protecting us from the charged particle, right. And the geomagnetic storms are correlated with the flares with the some time delay, right. So, flare happens, we see the geomagnetics, earth magnetic field is changing, but there is a some time delay, right, because this is storm, whatever happening on the sun will take some time to arrive at earth. Although the CME, which is one of the, you see this in the quiz also, the movie I say this large explosion from the sun and traveling into the interplanetary medium, that was not observed until 1970. Okay. So, first observation was also done in the radio. So, this is the where the sun disk should be. In the radio observation you see the blob of the plasma which is moving away from the sun, right. So, this was the first kind of observation of the CME, right. So, what is the space weather in general, what we discuss, right. So, solar magnetic field eruption from the sunspot which trigger the series of events, for example, solar flares, coronal mass ejection, and after delay of few days CME collides with the earth magnetic field, right, and strong geomagnetic storms are take place. So, geomagnetic storms are now connected mostly with the CME. So, the CME, which is the cloud of plasma and the magnetic field which travel from the sun and arrive at the earth, right, that are connected with the geomagnetic storms, right. Magnetic reconnection. So, earth magnetic field and the solar magnetic field which is coming through the CME, they connect with each other, they change their connectivity and the line, right, and then the charged particle enter into the polar region and generate the auroras, okay, which I would able to, so whatever I have shown until this many slide can summarize into this 3 minutes video. I do not know if the audio is. So, what it shows is this just general explanation that how the energy is generated. So, in the next few seconds it will show that at the interior of the sun where the temperature is very high, right, where that the protons basically fuse, create a helium, and then where this Einstein's famous equation E equal to mc square come in the place. So, these are the protons which collide with each other and generate the helium atom, and that is how the energy is generated at the core of the sun, right. So, these are the 4 protons, they come, collide, create a helium, and then the energy is released, right. Now, this energy would generate in terms of the gamma ray photons and will try to travel. So, they travel into the convection, and this are this convective cells, big convective cells, right, how this bubbling upper atmosphere which transport the energy to the surface, right, something like that. And then they generate the magnetic field. So, sometime this magnetic field which is generated, so plasma, the gas is the plasma body, right, is a conductive medium. So, when you move this current it can generate the magnetic field. So, when this magnetic field appear on the surface, right, it is one foot point, it is connected from one sunspot to another sunspot, and sometime they get twisted, and when they get twisted like a rubber band they can reconnect here, and this cloud of magnetic field is now detached from the main sunspot and now start traveling into solar system. So, now it start traveling into the solar system. First it will pass through the, so these are the flares, for example, this is explained. So, this is the magnetic loop which is got twisted and then it released from the surface, right, and then it will travel to the interplanetary medium. So, this is like that, it is traveling now, this cloud of plasma and magnetic field. First it will interact with the Mercury, if it is in the line of moving in the line of Mercury, right, it will interact there, it will pass through, right, and then it will go through the Venus, right. So, it will go through quickly through the Venus, and then it will, so this is Venus, it will pass through there, and then it will come to the earth, right. Now, you pay attention what is, when this magnetic cloud coming to the earth, what exactly is happening, right. So, when it is arriving, when it is arriving toward the earth, now earth has a magnetic field, right. So, earth's magnetic field is connected from here to here, right. In the back side it is longer loops. Now, this magnetic field direction, if it is opposite, right, you see this arrow are opposite, whenever they are opposite they will reconnect, some charged particle enter, right, in the atmosphere. Now, this magnetic field line move backside, right. So, these lines they have opposite direction to each other, they will reconnect here also, then the plasma will enter from here again from the backside, right, and then they arrive around the pole, and that is how the auroras are created. Okay. This is how the auroras are created at the pole. Now, if the event is much more bigger, this aurora can also come up to the lower latitude. Right. So, now as I explained it, the space weather could have a lot of impact. For example, our communication, right, aviation can be, because aviation depend on the radars, GPS signal basically. So, GPS signal is basically, right, you have a multiple satellite and their signal pass through, and then you identify your position, right. But their travel time depend on the ionosphere, right, and if ionosphere is lot of electrons ionized because of the more radiation, that delay will happen and your GPS signal might be not so accurate, right. For example, submarine, and then the under the pipeline, current pipelines can be affected, right. In the grids, electric grid, if there is a lot of additional charge particle, that would induce the more current on the electric grid, which is they are not designed for, right, and there is no proper distribution system. Modern days we have a better distribution system. So, if they do not have a proper distribution system, then they will be overwhelmed with the extra current, right, something like that. So, we know that this kind of event happened where there is a lot of communication and the technology, and we rely on the technology, right. Nowadays the satellite, right, electricity, communication, and it's $1 trillion right, economy. And suddenly if I say that every communication is dropped by the 1 minute, your stock market, your businesses, right, your communication, everything will break down, right, and it could have a completely adverse effect, right. It can destroy, which would be much larger than the pandemic kind of economic meltdown, right. So, we know that this kind of event happened in the past, not such severity, but in 2003 there was a Halloween solar storm, and this is where the aurora was seen in that event, and there you see that only I want to show is the magnetic field. During that storm, the Earth's magnetic field has fluctuated quite a lot, and that time lot of things happen, right. So, satellite based system and the communication were affected. Aircraft were advised to avoid the high altitude near the polar region. So, flight which are going over the pole, they were stopped actually. 1 hour long power outage was happened in the Sweden, right, and aurora was observed to the Texas, which is very low latitude. 12 transformers in the South Africa were completely disabled and had to be replaced despite the country's low geomagnetic latitude. So, South Africa is not so close to the pole, right. Even then this event has basically knocked down few transformers, right. Some other event happened, for example, I do not want to go into the detail, I will just move. Another famous event happened in 1961, which was the nuclear war alert, because that time the understanding was not so good. The surveillance radar on far northern part of the globe, for example, in the Alaska, Greenland and UK was jammed, right. And then this was thought, oh, it is maybe somebody else which is jamming our system, right, and that thought the nuclear attack might be happening. So, it was almost up to the age where this people who had the station here want to retaliate and launch the nuclear weapon. So, if you do not know, it can also lead into some human errors, right. So, this knowledge is very important, right. And this is in 1898, this is just one of the burned transformer during the solar storm, right. And recently, if you know that the Starlink, again it was in the puzzles, there was a strike of the satellite in the sky, right. This is the Starlink satellite which is used for the internet, and Elon Musk launched, and the 40 satellite of the Elon Musk was lost because of the geomagnetic storm. He is thought to be a very smart guy. So, every time they launch the satellite, right, they look into the prediction, right, what kind of the storm would be there, what kind of effect it would be there, but his team had made a mistake. They used very outdated model for the prediction of the yes.
What is an M1 class?
Yeah, this is I explained in the earlier that this is the different energy of the flare. So, flare are classified into the X, M, A, C class flare depending on how much X-ray radiation they emit. So, X class flare are the very strong flare, right. The M class flares are little lesser energy than the X-class flare. So it was not even the X-class flare. Thank you, you pointed out. It was M-class flare. The 40 satellites were knocked out. And again, because he did not use, the Starlink did not use for the prediction of the geomagnetic storm much more advanced solar models, because physicists have a much more advanced model, and if we would have used those models instead with the outdated models, he could have predicted that was the not right time to launch. Okay. Now, I just want to go not too much in the detail that this is about the solar physics and the space weather, but what we are as a nation doing to understand the sun and its working and its impact and all these things, right? So I will go a little bit historical. So you might have heard about the Kodaikanal Solar Observatory, right? And history of the solar astronomy in India is basically linked with the history of Indian Institute of Astrophysics, right? And the Kodaikanal Solar Observatory is the part of it. This year we are celebrating 125 year of the Kodaikanal Solar Observatory. So this observatory is almost more than a century and quarter old, right? So it was basically the precursor of the Kodaikanal Solar Observatory was the Madras Observatory. It was established in the 1886, but then realized that the British establishment thought that we need a better site for making the observation. So they were searching for a better site, and they found that the Kodaikanal is a very good location, very clear sky. You can observe much better on a regular basis. So they have established the Kodaikanal Solar Observatory in 1899, and this is what the 125 year of since 1899. And later, when the Indian Institute of Astrophysics or Indian Institute of Astrophysics was established with the Kodaikanal Solar Observatory, Kodaikanal Solar Observatory has become the part of the Indian Institute of Astrophysics, right? So there we have been observing sun almost on the regular basis for more than 100 years, right? But when you think about the 100 years back, what kind of technology was available 100 years back? We did not have a digital cameras, right? So that time the images were taken on the photographic plates. So this is the photographic plate, okay? And now our institute has digitized all of the photographic plates. So this is the same image digitized. Now this line has been tilted. You see the sunspot which are 2 point here, right? So now you have this 100 year of data, for example, in this particular. So this is called the white light, where you see the photosphere. You can observe in another line, which is the calcium line, right? Again digitized. Now you see the much different structure what you see in this image, right? So this is the more of the chromosphere which is above the photosphere. Now you see the filament in the H alpha line. So this is the hydrogen line, right? Again digitized. So this have been observed. You see that this is the latest in terms of these three images started later, 1912, but is already more than 110 years or more, right? So you observe. So we now, okay, we are observing for more than 100 years. What use of it? Now, so I explained, right, that sunspot has this long-term variability, right? How the magnetic field is generated, right? So this is one of the oldest observatory in the world, right? So this kind of data where you will able to plot for more than 100 years, only few observatory have such kind of data, right? So where you can plot the number of sunspot, you can see that why one cycle is stronger than another cycle. This is the same plot which I explained. So you can use this data and try to understand how the magnetic field is generated, what are the processes taking place inside the sun, can they predict this kind of observations or not, and you can verify your model and study that, right. So this data is very valuable. A lot of research publications are done using this data, and a lot of people are also using this data, not just from India, but international scientists are also using this data for their research. So then you must all have heard about the Aditya L1, right. So that was launched in the September last year, right? And this is just the launch video. This is just to get a sense of how the satellite is. So these are in the assembly, in the satellite integration, and these are the people who are involved in the integration, and you see this is the satellite. So how big is the satellite compared to the human size? You can get a scale from there, right? And it reached to the L1 point in the 6th January 2024. What is the L1 point is basically the point. So this is sun, this is earth, and the L1 point is in between. So this now has reached on the 6th January this year there, and is orbiting in this around this L1 point, and this is where the gravity of these two bodies and the force from this rotation balance up. So, this satellite always stays there, and why it is important to be there, because whatever happening on the sun and traveling toward the earth would be detected here, right, and we will be also able to make the images of the sun same time. So, with the remote sensing you make the images of the sun, but also any magnetic field changing here, all the charged particle which have arrived would be detected here as well. So, this is called the in situ measurement. So, like we measure the temperature here, the same way it would able to measure the property of the magnetic field charged particle at this position. So, it has a 7 different payloads or the instruments. So, for example, coronagraph, which you have seen the images, how the coronagraph, it's occult the disk and see the surrounding corona, which is not as bright as the disk, right. And then the images, the image of the full sun in the ultraviolet light, which is the suit. So, this is built by Indian Institute of Astrophysics in Bangalore. This is built by the IUCAA in Pune, and then there are other payload, for example, X-ray. So, measure the X-ray radiation from the sun during the flares. There are particle experiment which measure the particle where the satellite is orbiting. So, whatever particle arrives where the satellite is orbiting, it is measured there, and then the magnetic field where the satellite is, right. So, I just wanted to show some of the images, right. So, this is the ultraviolet image made from the suit, and this is the corona. So, you see the bright corona at the occulted here. So, the black part is the occulted region, and then this bright part you see is the from this VLC instrument the measured corona. There are a lot of data which is still being processed for all the payload. Now, people has started looking into what is the science can come out of it. So, maybe in the 6-month time or year time, the more scientific result will start coming out from this mission. This is the X-ray. So, this is, you see these curves, these top two curve, this is the X-ray with the time. Top two curves are the NASA satellite, and the bottom curve is the India's Aditya L1, where it measure the X-ray. You see that first thing is to confirm that whatever we are measuring, it confirmed by also measured by other satellites. So, you see that wherever there is a flare, you are able to measure them, but you also see that whenever this peak was very small in this NASA satellite, we have a much more clearer peak, right. So, in certain extent, we are also able to do better than what was done previously to detect a very small flares as well, which were the existing X-ray measurement were not able to detect it with such accuracy, right. And now, come back to the earth, right. So, when I showed this very high resolution bubbling image of the photosphere, right, that are taken from the ground based telescope, right. So, we want to build this National Large Solar Telescope in the Ladakh area. So, this is the Pangong Lake. You have, many of you have seen 3 Idiot movie, right. There is this Pangong Lake where the climax happen of the movie. This is the same lake where we want to establish this telescope. Why close to the lake? Because the Earth's atmosphere has a turbulence, and when you are close to the water body, this turbulence get reduced, right. So, when you are walking in a hot summer day on a road which is empty, not possible in Bangalore, right, and you see that the scenery in far would be moving, right, because the gas basically is turbulent, the atmosphere is turbulent in between. Same happen all the time, right, when you are looking at the sun. So, the images would be moving and not sharp, right. So, this is what we want to build, right, there. So, what is the National Large Solar Telescope? So, this is the 2-meter primary. So, every telescope either has a lens or the mirror, right. So, we use this want to build this 2-meter telescope. So, currently largest telescope is around 4 meter, which is the DKIS. 2 meter we want to build. I do not want to go into this one. So, this is the largest solar telescope right now, which is in the Hawaii, right. But from the ground you can only observe, right, you can only observe. So, this is just the design of the telescope. I do not want to go into the detail. So, this is the big telescope in the Hawaii, right. But now you see that during the night, of course, you cannot look at the sun, right. So, somebody has to observe from the ground. So, there are other European Union want to put a telescope in the Canary Island, but we want to fill the gap. So, we will be able to observe the sun 24 hours continuously, right, also from the India, right. So, that it will fill the gap, because apart from, in space you can always look and every time you can make an images. Ground has a limitation because it would be cloudy, rainy, so you will not able to make the observation all the time. But then you will ask question that what is the sense of observing then from the ground, right? But you cannot big such a big telescope. You can send a big telescope in this space, but it's extremely costly, right? And you can learn a lot of instrumentation, how to build the telescope and those things when you first do on the ground. When you learn the technology, you advance and go into the space, right? So this is very important, right? So this is, I just leave you with these images. So at that particular site in the Pangong Lake, we already have this small telescope. We make the images like this on the almost daily basis, right? And I leave you with this beautiful movie which is called the Coronal Rain. And if you have a question regarding this, you can just ask me. Yeah. Okay. So thank you very much.